The 8 basic trig identities can be combined and put together in different ways to create more complicated trig identities. These are the 8 basic trig identities. 3 of them come from the Pythagorean theorem. They're known as the Pythagorean identities. 3 of them are known as the reciprocal identities because they're saying that one thing is the reciprocal of the other. And then these other 2, this tangent one is usually the first identity that people learn anyway, and cotangent is just because cotangent is the reciprocal of tangent. Truth is that even if you only had 4 of these identities, like you basically just had this one Pythagorean identity and this tan identity, and then all 3 reciprocal identities. Even if you just knew, or I should say, if you just had these 5 and that was it, you could get the other 3 pretty easily. Here's what you would do: if you take this first one and you divide both sides by cosine squared, then you can say, well, since secant's 1 over cosine squared, this becomes secant squared. And since sine over cosine is tangent, this will become tan squared. And since cosine over cosine is 1, and you see we'd recover this one. If you divide both sides instead by sine squared, you'd end up with this identity. So here's how you could use those identities to create other ones, like tan over secant. That can actually, one technique is to use the 8 identities that are known to do anything you can, really. So like tan x can be replaced with sine x over cosine x, and secant x can be replaced with 1 over cosine x, and then I can sort of multiply by the reciprocal and cancel, and I get a new identity that tan x over secant x is equal to sine x. So this is sort of simplifying an identity, or just changing it, changing one expression into an equivalent expression. Here's one, cosine x over 1 minus sine squared x. Now, one of the identities this one here, it could be rearranged. You could change it into, you could subtract cosine squared from both sides, get sine squared theta equals 1 minus cosine squared theta. Or instead, you could start over and subtract cosine squared theta, so sine squared theta from both sides, get cosine squared theta equals 1 minus sine squared theta. Even though these 3 are all variants on the same identity, these 2 versions of them get used frequently. So right here, I have the opportunity to replace that with cosine squared. Then I can cancel out one of these cosine x's with one of these. I get 1 over cosine x, and then there's an identity that says that secant is 1 over cosine x. Another one. Here I have the 1 minus cosine squared x. That gets replaced with a regular sine squared x. I'm using x instead of theta. Easier to write. And now I can, whoops, that's sine x. I can cancel out one of these with one of these, and I'm left with cosine over sine, which is an identity for cotangent. I think for this one I'd use FOIL and see where it takes me. Here I have this complicated sine x, secant x. I'm hoping that becomes something nice. Minus sine x, tan x. So the secant x, leave that alone for now. I'm interested in these. Sine x, secant x is the same thing as sine x times 1 over cosine x. which is the same thing as sine x over cosine x, which is tangent x. And sine x tan x is the same thing as sine x times sine x over cosine x. So looks like sine squared x over cosine x. So it's getting kind of ugly, but if I take these sines and tans, and this one here, which is a tan now, well, first of all, these two tans cancel out. So now I have secant x minus sine squared x over cosine x. Secant x is 1 over cosine x minus sine squared x over cosine x. Common denominator, that is. And this 1 minus sine squared can be replaced with cosine squared x, and then the cosine x in the denominator can get canceled out with one of the ones on top. And this whole thing ends up equaling cosine x. Now in this one, it's very tempting to replace this numerator with cosine squared x because we have an identity for it. But that really wouldn't get us anywhere. We'd kind of be stuck at that spot. So instead, I'm going to notice that 1 minus sine squared x can be factored. And this is a trick that you kind of look for. And this is really convenient because the 1 minus sine x cancel out. And I'm finished. Oh, there was a minus 1 in the question that I neglected. So put that minus 1 at the end. And then you get 1 plus sine x minus 1 is just regular sine x. And for this one, there's not much you can do. The only thing you can do is combine these fractions, getting a common denominator. So the common denominator will be complicated. It will be cosine x 1 plus sine x. They don't have any common factor or anything. And you kind of cross your fingers here. So the numerator needs to pick up a 1 plus sine x. And the numerator here needs to pick up a cosine x. I'll put cosine squared x. And it's getting pretty ugly. Let's see what happens. Distribute the sine x there. Sine x plus sine squared x plus cosine squared x. And here's a nice thing that happens, which is that this sine squared plus cosine squared x, that is one of the identities. It equals 1. So if I replace that with a 1 here, and then as an added bonus, I now have sine x plus 1 on top, and there's a 1 plus sine x on the bottom. Those can be canceled, and I'm left with 1 over cosine x, which turns into secant x. So these two things, these two expressions are equivalent to each other. And that's some techniques for how you use the 8 basic trig identities to get other identities. One technique is change everything to sine and cosine, see what happens. One technique is to if you notice 1 minus cosine squared or 1 minus sine squared, to substitute and cancel, multiplying out, and then changing things to sines and cosines. Factoring 1 minus sine squared instead of changing it into cosine squared. And getting a common denominator and just being real careful. You don't want to make a mistake because it won't work out. You won't get trig identities to substitute things for.